Hey everyone, welcome back to the channel, and in this lesson we're going to be talking about a couple of different things. We are going to start out with the announcement of a new project for you guys, and so this one is of course going to be based on astronomy, and it's going to be related to the last video, the really long one where we talked about the planets of the solar system. And I'm going to get into the details of the project first, just because I'd like you guys to have all the information that you need right off the bat. And then after that, we will transition into the main topic of the lesson for today, which is on the Goldilocks Zone, which is something that you may have heard of before. If you haven't, that's okay. We're going to talk about it in today's lesson. I'm going to try to keep the lesson shorter than it was last time, like more of a one lesson per class kind of length rather than, one lesson that spans 3 or 4 of your science classes. So I've tried to keep it shorter just so that I don't ramble on for quite as long. If it ends up being too short, then I'll fix that for next week. But let's get started. So your project in the astronomy unit is going to be all about space exploration. So in the last lesson, we talked about the different planets in the solar system and a few interesting facts about them, or their moons, where they're located, their orbits, things like that. Now, some of those things were discovered by scientists that were sort of churning out the math, pen and paper, or in computer simulations for things like orbits, to understand how the different planets move, how far away they are. Some of those things, you figure them out without actually sending anything out into space. But for other things, like getting high definition color photos of them, you need to send something actually out to those planets, because from here they're too small. You can take pictures of them, but they're not going to be as HD and as detailed as you would like them to be if you're taking a picture from a telescope that's on the ground or even around Earth, like in orbit. The best way, if you want to get some really, really good information, is to send something there. So this has happened many, many times. If you just go on the Wikipedia page for like list of space probes or something like that, or list of solar system probes, you'll see that there are tons and tons and tons of probes that have been sent out into space to explore various parts of the solar system. So there have been some missions to the inner planets, some to the outer planets, some to asteroids, and there are even a few probes that have actually left the solar system. And so lots of these kinds of missions involving space probes that actually go to a planet or an asteroid or whatever to get some really detailed information on site. Lots of these missions have happened, and if you go on Wikipedia again and you look at all the missions that are there, a lot of them have failed. So it's not that easy to get a space probe from point A to point B if those 2 points are 2 completely different planets, right? It's not always the easiest. If you do some digging on the sheer number of probes that have been sent out into space, you'll see that there are a bunch where the problems that they had were things like couldn't get out of Earth's orbit. Like there were problems that just at the launch or just after the launch, they weren't actually able to leave Earth properly. So that was back in the days when, we're still learning what to do to get these probes to go out into deep space sort of more consistently, right? So if you look on any list of the probes, you'll see how many of them have failed, but also a lot of them have succeeded, and they've yielded some very, very useful information to us. Primarily to the scientists that are studying those planets, but some of that information will trickle through and the general public learns some of those things. But basically, the science research teams that are studying the different planets or asteroids or whatever, they get tons and tons and tons of amazing information from these probes and from the pictures that they take and from the other kinds of data that they're able to collect. And so what your task in this project is going to be is you're going to explore a little bit, sort of peeking under the hood into how scientists were able to learn so many things about all the planets. So we're not going to just kind of look at the entire process of, how do you build the probe and when do you send it and where do you send it and how do you time it right so that it's going to get there in the least amount of time. And we're not going to look at all of that. What we're going to look at is each of you is going to choose a specific mission, a specific space probe that has gone out into some part of the solar system or another. And we're focusing on exploration of the planets, but if you're interested in, something that's gone to an asteroid, for instance, then let me know and we can totally work something out there. But so, for example, you'll take a space probe. I've got on the slide here Voyager 2 as an example. Voyager 2 is an option. Pioneer 10 is an option. Things like that. So let's say you pick Voyager 2. That's the name of a space probe. Let's say you choose that as your mission that you're going to study. So what your task is, you're going to look up what instruments, so what different scientific equipment was placed on board the space probe and what those instruments do. Or you can see I've put the present tense and the past tense because for some of these probes, either humanity's lost contact with them or they crashed or, they're just not active in some way, shape, or form. And so what you're going to do is you're going to look up which instruments are or were located on the probe and what those instruments did. So we're going to talk a little bit more about this on the next slide or the slide after that or something. But basically, you're not overly concerned with the names of the instruments because honestly the names get really confusing and they have some really long words and they don't really paint a clear picture of what they actually do per se. I mean they obviously paint a reasonably good picture, but it's in scientific jargon that most everyday people wouldn't understand. And honestly, even I'll look at some of those names after 5 years of studying physics and I'm still not getting a full picture of what exactly is going on or what kinds of data these different instruments collect. So you're not going to be worried about what the instruments are called or what they look like necessarily, but you're going to research what those different instruments do in plain and simple language. You could find that on the internet. You could find it specifically on YouTube, a YouTube video that explains the different components of a specific probe. And so that's going to be sort of one of the two main parts of your project is going to be understanding what the different pieces of equipment on the space probe actually do or did. You're also going to include just a little bit of background information, just, for the sake of completeness. When did the probe launch? Who launched it? So what country or what space agency? As you look through, if you do look through a list of missions, I've included a list of missions in here for you guys to choose from, but if you want to do a little bit of sort of background reading on a few of them before you actually choose which one you want to study, then you'll see that it's overwhelmingly the Americans and the Soviets, the US of today and the Union of Soviet Socialist Republics, the USSR from, several decades ago, that did a lot of the work in sending probes to other planets. And so you'll also see, if you go and look, you'll see all the failures from both sides. But that was sort of, that was the time of the space race. So these two countries, the US and the USSR, they were competing with one another to get, to be the first to reach certain milestones in space. So first man in space, first woman in space, first orbited the Earth, first dog in space, first probe to orbit another planet, first probe to land on another planet. And, of course, there was sort of the crown jewel of first man on the moon. But so that's just for this background section of when did the probe launch, so what year. You don't have to be super specific with the date, but just a rough idea of the year so that we can sort of piece together a timeline once we've all gone through it. once we've all gone through our presentations, and who launched it, so which country or which space agency. And then the main part of your project is going to be on what did this mission actually teach us? What new things were discovered by going on this mission to another planet? By sending basically a robot into space to another planet. It took some pictures, collected some data. Not all of it was going to be through pictures, obviously, but collected a bunch of data, magnetic field strength, and obviously some photos, and then photos in other spectra, so like an X-ray photo or something, and just to see how different does it look. If I take a picture of a person and then I take a picture of the same person but in infrared light or something, it's going to look like a completely different picture, and you'll get different information. Even though it's two photos, you can have a photo that's the way our eyes see, and then a photo that's in infrared or ultraviolet or something, and you'll gain different information from that. So your job, the main part of your project, is going to be to talk about, so you see it kind of links back to what the instruments do. So you're going to talk about what the instruments do, which ones were on board and what they did, and then how those instruments were used to discover all the things that were discovered. So you're going to talk about what was discovered, which instruments would have been used to discover that. If it's not easy to make that connection, that's okay, but you should at least make sure that you talk about which instruments are on board and what we learned from the mission. So if you send a probe to Jupiter and you discover something like the Great Red Spot, for example. Suppose we didn't know what the Great Red Spot was, and then you go to Jupiter and you see this massive red storm in the middle of the planet. That would count as something that was discovered. But of course, it's big enough that we knew it was there from before. But so things like that, if there's something new that was discovered about the object that was being studied, about the planet that was being studied, then include that in your project, in your presentation or poster. So there's going to be a poster/presentation project. So you can make a poster if that's more convenient, or you can make a presentation. I still haven't worked out all the details of how exactly I'm going to have you guys present that. Like, are you going to send it to me? Are you just going to present it amongst yourselves and have me grade something extra? I haven't worked that out yet, the details of the grading and stuff and the due date, but the idea is a poster or presentation on this. And the other things that you want to include are some photos, because most of these missions would be accompanied by photographs of the planets that they went to. So include those either on your poster or in your presentation, and just talk briefly, again, just for closure. We talked at the beginning, when did it launch and who launched it, and at the end talk about how did the mission end. So the mission could have ended if the probe crashed or if we lost contact with it. In some cases, you'll see that the official quote-unquote mission ended at a certain date, but the probe still exists and we're still in contact with it. It's just not really it's not doing the grunt work. It's on vacation. It's out in space and it's not doing the work that it used to do. It used to collect all this data and send it all back, and it was this primary area of research and focus. And now it's there and we still talk to the probe, but it's basically on vacation. It's not really doing as critical work per se anymore. So in that case, you could give all of that information. You could say that the mission officially ended on November 1st, 1991, but the probe still exists and here's where it is today, and we still talk to the probe and all that stuff. So you could include all of that stuff. The more the better. And yeah, let's move on to the next slide. So what you can see on this slide here is a list of the missions that you can choose from for this project. Now, it's not an extensive list of all the projects, of all the space missions that have ever been sent out there, but it provides a reasonably decent balance, I think, of missions that have visited various planets in the solar system, and so you can choose from sort of any one of these, or in some cases you could choose from. So in the case of some of them, I've kind of left it up to you. If you want to pick the Venera probes, which are part of an old Soviet program, I'm kind of leaving the door open to you. You could study just one of these four. You could study all four of them, because the thing is, if the missions are all sort of numbered in a sequence, chances are the probes have sort of the same kind of goals and maybe some of the same equipment from one mission to the next to the next. So I'll leave the door open to you if if you're really fascinated by the Venera probes, if you really like Venus basically, and you really want to study the probes that have been sent to Venus. I'll leave you the wiggle room to decide whether you want to study one of these four or one of the other ones that's not here. I picked out a few that have had some significance of like being the first one to actually land or having survived on the surface for a really long time compared to the others. Things like that I've included for picking these four in particular. But if you want to study like Venera 4 or 9 or 10 or 12 or something, go right ahead and feel free to look through that. The only thing I ask for, of course, is don't pick a mission that failed. So I don't know offhand which ones did and didn't work, but if Venera 1, for example, was unsuccessful, then maybe don't pick that one, because as much as you could talk about the equipment that was on board, you can't talk about what we learned from it because the mission failed, right? So do try and pick something that there's actually something to talk about, and I do believe that everything on the slide here would give you something to talk about in terms of discoveries that were made. And you can see in brackets I've listed the planet or planets that were visited. It's not necessarily the most extensive list, because there would be some probes that flew by Venus and then went out into the outer solar system to Jupiter, and so I haven't included the name of every single thing that might have been visited on the way, but this gives you a rough idea, and every planet is mentioned at least once, not counting Earth, because we didn't send any probes to explore Earth. So obviously taking Earth out of the equation, we got Mercury here, we got Venus here, Mars, Jupiter, Saturn, Uranus, Neptune, and even one mission to Pluto. So this is a sample of the missions that you can choose from, but like I said, if you want to choose something else, feel free. Just let me know, and so that we're on the same page. I've included a bunch of missions where their planetary exploration stuff is done. So you'll notice I included Spirit and Opportunity, two rovers on Mars, but not Curiosity, because we're still learning new things from Curiosity. So if you want to study Curiosity, that's fine. Let me know, just so that we're on the same page. I just picked a bunch of missions where all their work is basically done at this point. At least in the studying planets department, all their work is done, just so that everybody's kind of on a level playing field of that your presentation doesn't become outdated 2 days before you're supposed to present because some new discovery has been made. So that's why I've picked a bunch of missions where all their work is done. One thing I would like to warn you of as you're doing a little bit of reading before you choose your mission is be aware that the older the mission is, it's probably going to be harder to find reasonable information on it. Like it's going to be harder to find information that makes sense, that's easily accessible. Like if I go onto YouTube and I want to learn about Voyager 2 or New Horizons, these are either relatively important, like Voyager 1 and Voyager 2 explored so many planets and taught us so much about the outer solar system. That's not to say that these ones aren't important, but if you've only gone to Mars 40 years ago, that's different from going to 4 planets 40 years ago. So you'd find more information about this. New Horizons is very recent. That was in the last 7-8 years that it reached Pluto. And so there's tons and tons of information on New Horizons on YouTube. But the Venera probes, maybe not as much. Mariner 10, maybe not as much. Mariner 9, Mars 3, you're not going to find as much information on these probes as readily, I don't think. But with something like New Horizons, whoever picks New Horizons, I'll tell you right now, there is a ton of information on it on the internet because it reached Pluto in the age of YouTube. So there are tons of people that in 2013, 2014, 2015, leading up to the flyby in July 2015, speculating what's it going to see. These are these are the things that we might see. These are the instruments that might give us that insight. And so there's tons of information for New Horizons and for the Voyager probes and the Pioneer probes. I personally have not spent that much time looking into these ones. My fascination was always with the outer solar system, so I do tend to know more about these 5, I guess, than most of these. But the choice is ultimately yours. Just be aware that if you choose a mission from the 60s or the 70s, you might have a harder time finding relevant information compared to somebody who's picked a mission from the 80s or 2015, right? So just before we move on, I do want to give you a warning that when you're researching the space probes and the equipment that's on board, you might come across some really complicated or scary words, something like photopolarimeter. And that word will most likely mean basically nothing to you while you're reading it, right? So if you say this probe has a photopolarimeter on it, it's like, I don't know if that gives you any information. I don't know if that gives your classmates any information when you're presenting. So don't worry too much about remembering the different names of the instruments. Focus more on what they actually do, right? So if there's a I don't know, like if there's a specialized camera to take pictures in a different spectrum, like an infrared camera or something, the camera might have some fancy name because it's an infrared camera. If you say it takes pictures in infrared and this is what the normal picture looks like and this is what the infrared picture looks like, that is a great explanation of this is what this instrument does, this is why it's useful, right? So don't worry too much about sort of all the technical details and the words and what they all necessarily mean. Just focus on what the instrument actually does. In some cases, in a lot of cases, you might find that the instruments have really long names and then they get shortened into easy to remember acronyms. So if you want to include the acronyms, go for it. If you want to include the full names, go for it. But don't include just the full name or just the acronym and leave it at that. Do focus on what the instrument is actually doing, right? So that if I asked you to pick which instruments you wanted to put on a space probe, it's less important that you know what Pepsi stands for, Pepsi with 2 S's. It's less important that you know what Pepsi with 2 S's stands for than it is to know what Pepsi actually does, what the instrument actually does. Because then you would actually be able to say, it's like, okay, well, if I want to get this information, if I want to take this data, then I can use this instrument because that's what it's made for, right? So focus on what the equipment on board actually does. So in general, here's what you need to do. You need to pick a mission, probe, whatever, from the list a couple of slides back. You should be watching this on a Friday. I'm okay with you not having your probe picked out by the time that you're watching this because for most of you, you probably don't know very much about most of the probes. Even I don't know very much about several of those probes because I just haven't looked into them, didn't study them, whatever. So I'm not expecting you to be like, oh, I want to study the messenger probe. You don't know when it was launched. You don't know anything about what it discovered, how useful it was. And then you say, I'm going to study the messenger probe. And you go home, you go online, and it's the most boring probe that you could have picked for your interests. It's like, oh man, I really should have studied Pluto or Jupiter or something, and I got stuck with Mercury. Like, there's nothing wrong with the messenger probe. I'm just using it as an example. So I'm okay if you don't just pick your probe willy-nilly today while you're watching this. Feel free to take the weekend, just read through sort of like a Wikipedia article of 5 lines of what each of them does. The first paragraph of each probe's Wikipedia article. and pick which one is the most interesting to you. Scroll down, look at the pictures that were taken by the probe. If you go into the Wikipedia article for any of these probes, you'll see the pictures that they took and the kinds of stuff that they discovered. Pick the ones that are most interesting to you. Now, of course, if you're making your selections over the weekend, you might want to have a couple of backups ready in case a bunch of you want to do New Horizons, since you all heard that it was made during the age of YouTube, and so there's a lot of information. So don't just put, okay, New Horizons, that's my first choice, and then just stop, because there might be 3 other students that all want to do New Horizons as well. So have a backup that, okay, it's like, okay, I wanted to do New Horizons, but I kind of like Voyager 2, so I'm going to do that one instead. And if somebody else has picked Voyager 2 and I don't get that one, then I'm going to do Voyager 1, then I'm going to do Pioneer 11, then I'm going to do Pioneer 10. Have a list of 2, 3, 4, 5 probes that you'd like to do in order, and then you guys can sort it out either on Monday during a break or next Friday in class. Figure out who wants to do what. The earlier the better, just so that you can start actually researching earlier, because there are several questions that I would like you to address in your project, which is, like I said, either a presentation or a poster. So you should be sure to include what instruments are or were on board, and what do they do, or what did they do. When did the probe launch, and also who launched it. What did it teach us? So what was found out that we didn't know before we sent the probe out. This should be the main focus of your project, and you can tie it into what instruments were on board. If you want to talk about, we discovered this storm on Saturn, and we discovered it using this camera, which we talked about at the beginning of the presentation. If you want to tie those things together, you can totally do that, and I recommend that you do. But your main focus should be, what did we learn from the mission? And your sort of secondary thing should be, what instruments were on board and what do they do? Because the rest of it, when did the probe launch? That's just sort of like a little intro thing at the beginning. How did the mission end? That's just like a little conclusion outro thing at the end of how did the mission end? When did it end? Just to give us a sense of the time scale. And of course, feel free to include lots and lots of pictures, because that's sort of my favorite part, and probably most people's favorite part of reading about space probes and their trips into space, is seeing the pictures that they sent back, especially if it's pictures of the planets. If it's pictures of an asteroid that you've never heard of, that's got a really long, complicated, computer-generated name, then it takes a little bit of the fun away. But if you go, oh my god, that's what Neptune actually looks like, that's amazing, throw in a bunch of pictures of Neptune. That's totally fine. Those are sort of the 5 main things I'd like you to focus on. If there's anything particularly interesting or special that you found especially intriguing while you're doing your research that doesn't fit cleanly into one of these 5 categories, that's fine. Feel free to add it in anyway. Anything that you find interesting about this, if you want to sprinkle in a little humor, a little meme here or there, that's fine too. But focus on these 5, and then anything else that you find interesting. And for those of you that are interested now or interested once you start the project, there's a bonus task here for you, which is that either at the end of your presentation or in some part of your poster, come up with an outline for an idea of a space mission of your own. So which planet would you like to send your probe to? And what instruments would you put on board? What would you hope to learn from it? So basically design your own space mission. It doesn't have to be to the same planet as the one you're studying. You could, for example, pick a probe that studies Jupiter, right? That studied Jupiter at some point. And you say, oh, so this instrument takes this kind of data, which teaches us this about Jupiter. Now, I'd be interested to know whether we have that kind of information on Saturn, whether we have that information about Saturn so that we could compare. And then you go look it up and you see, oh, we don't have that information about Saturn. I would love to send a probe with this instrument, but to Saturn, so that we could learn this property of Saturn and then compare it with Jupiter. So you don't have to pick a probe. You don't have to pick the planet that's the same as the one that you're studying. But it's just a little bonus thing. If you have time, if you're interested, come up with your own sort of mini space mission, you'll see when you do your research that the missions will have like 5, 7, 10, 12 different instruments on board. You don't have to go into that kind of detail if you do the bonus task. If you can come up with 2 or 3 instruments that you would like to have on board, you could say, I'd like to go to Neptune with an interferometer and magnetometer and whatever, and a photopolarimeter. Then that's great. Then you can, as long as you can explain why, then that's perfect. And the only reason I've underlined the word hope here, and what would you hope to learn, is that the missions don't necessarily work out perfectly every time. You might run into technical problems. You might just find something surprising. You might find that the thing you thought would be really interesting about Neptune turns out to be really hard to find, or you were looking in the wrong spot, or it's just not interesting. It's exactly what was predicted 300 years ago by some, you could say, what would you hope to learn? But you can't know, obviously. If you say, this is where I'd like to send my probe and this is what I'm going to learn, you don't necessarily know exactly what you're going to learn, right? So that's why I've underlined the word hope. But yeah, there's your project. Pick a mission or a probe in the next few days, ideally, and then start working towards the creation of a presentation or a poster where you discuss the instruments that are on board, what they do, when the probe launched, what we learned from it, some photos, and how the mission ended. And then obviously the bonus task if you are interested. And so this is just one, I believe, final note about this project for the time being. Don't stress out too much while you're reading about the instruments. I know it can be daunting looking at some of the names of the different instruments, or even looking at what they look like. There's a lot of technology packed into these space probes. So don't worry about learning it all super fast. You're going to have a few weeks to complete this project because I want you to have enough time to read about and digest what the different instruments actually do. Stay tuned for more details like how and when the presentation and poster are going to be due and marked and all of that. I haven't worked out those details just yet, but for now, suffice it to say, pick your mission, and then as you start doing your research, learn some of the background, why we sent it, who was in charge, which space agency, all that stuff at the beginning, and then focus on what discoveries were made, what did we learn from it, and what have we done with that information since then. So that's the most important aspect of the project. Aside from that, stay tuned for more details. I'll be sure to give you guys an update on when it's going to be due and how you should submit it and all of that stuff, because we're dealing with those the difficulty of online learning in this class. So yeah, don't worry too much about the nitty-gritty details of grading right now. Just focus on the learning. That's the most important thing. Pick your project and just start learning, and we'll see how it goes. So at this point, we are ready to talk about the main subject matter of this lesson, which, now that I've talked so long about the project, might spill over into your next class. But we are going to talk about the Goldilocks Zone. There's not a ton that I wanted to include here that I haven't sort of talked about before. So it's hopefully not going to take quite as long as what you might be used to by now. But let's dive right in. So what is the Goldilocks Zone? It sounds like a bit of a childish name for something that's, in the center of solar system type astronomy. So if you want a more official sounding name, you could refer to it as the Habitable Zone or the Circumstellar Habitable Zone. So the Habitable Zone means it's the area in which things can live or people can live or whatever, in which life can exist. Circumstellar is a fancy word for around a star. So what is the zone around a star in which things can live? That's what it means. That's what circumstellar habitable zone means, is the area around a star in which things can live. That's what that is. More sort of generally, it's the region around a star where a planet could have liquid water on its surface. But you can think of it as basically the region around a star where life can exist. Now, that's not to say that every planet with water on it is going to have life on it. And that's honestly not even to say that every planet with life on it, if there are other planets with life out there, that they have liquid water on them. It's just that based on our understanding of biology here on Earth, everything seems to depend on liquid water in some quantity in some time frame, right? Even the things that can go like, 10 years without a single drop of liquid water, after 10 years, they need a drop of liquid water for something, right? So everything that we sort of see on Earth depends on liquid water in some way, shape, or form. And so we can generally work off the assumption that a planet that has lots of liquid water has a good chance of having life on it, but it's not guaranteed to have life. And there is the possibility that life could exist without water, that we just don't know about that kind of life. Now, why is it called the Goldilocks Zone? Well, for those of you that are familiar with the story of Goldilocks and the Three Bears, this bit at the bottom of the slide here will seem like a nice nod to that story, to the story of Goldilocks. If you have a planet that's too close to its star, it's too hot, and the water that could exist on its surface boils off, and you just end up with steam, and it never forms lakes and oceans. It's just a bunch of water vapor that hangs around in the atmosphere or just straight up leaves the planet over a long period of time. So if you're too close to the star, it's too hot. If you're too far from the star, it's too cold. And so all the water freezes into ice. And so this is where, if you look at like the moons of Jupiter and Saturn, and moons like Enceladus and Europa, they're just coated with this shell of ice on the outside. Even Pluto, I mean, it's brown in color, so it maybe looks more like dirt than ice. But if you zoom in and you look at the surface, it's an icy surface, right? And that's to be expected of a planet or of an object that's so far away from the sun. That makes perfect sense. So the Goldilocks zone is that sort of just perfect, not too extreme in either direction. It's not too hot, it's not too cold, it's just right. And so that's very familiar from the story of Goldilocks, and so we call it the Goldilocks zone. So in a little bit more detail, what happens if you're too close to the star that you're orbiting? So obviously, if the closer you get to a star, the hotter the planet's surface is going to get, and so all the water on the surface will evaporate. The hotter it gets, all the water goes. You guys have seen this on hot summer days, or I guess for you guys maybe all the time, but definitely for me, hot summer days, all the water will just evaporate. If you pour a glass of water on the sidewalk, don't do that; it wastes water. But if you pour a glass of water on the sidewalk, it'll evaporate on a hot sunny day, whereas in the winter you pour a glass of water on the sidewalk and it'll freeze. So on this side, on the too close to the star side, it's too hot, all the water evaporates. So there's that problem that you're not likely to find life, at least life as we know it, because the life that we know is based on the existence of liquid water. So if there's no liquid water, chances are you're not going to find life as we know it. Because it's too hot for there to be any liquid water on the surface. Now there's this other interesting phenomenon that happens if you get really close to a star, which is called tidal locking. And this is a little bit difficult to explain without pictures, so I'm going to try to draw this to explain. I'm going to try and pick two colors that don't really have any sort of like resemblance to temperature. So I'm not going to use red and blue to denote like hot and cold. I'm going to use two completely different colors that don't mean anything when we talk about temperature. So let's say green and purple. And we don't know anything about whether the green side is the hot side or the cold side or whatever. So suppose we've got a planet that's got this interesting geology on its surface, interesting rock setup on its surface, where it's got a whole bunch of like green rocks on one side and a whole bunch of purple rocks on the other side. So it's a half green, half purple planet. And that's not a day-night thing. It's not a hot-cold thing. Actually, you'll see in a sec, it is kind of a day-night thing, but whatever. So it's just got this interesting surface geology where one side of the planet is green and one side of the planet is purple, and there's this line down the middle, right? Now suppose you put your star here in the middle, right? So here's your star, nice oval star, right? So we've got a star here in the middle. Let's make it a little happy sun. There we go. And so we've got our star here in the middle, and as the planet orbits the star, normally if you consider a planet like Earth, we've got, here's Earth up here, and we've got our axis of rotation, and the planet spins around its axis every 24 hours. That's one day, right? And then it does that 365 times while it's going around the sun and coming back to its starting spot, right? So if the sun is like right here, then you have the Earth spins around on its axis once per day, and then it does that 365 times while it's going around the sun and comes back to the same place that it started at. And so we get that, you know, you have 24 hours is one day, and then you have 365.25 of those days in 1 year. In the case of a planet that is tidally locked, what happens is the amount of time it takes for it to spin around on its own axis once is the same as the amount of time it takes to go around the star. So basically, its day is just as long as its year. So instead of having 1 day equals 1 day, but 1 year equals 365 days, you'd have a day is, for example, a day is 24 hours, but then a year is also 24 hours. And so this happens because of the forces that the star exerts on the planet, slowing down its rotation and stuff. But the interesting phenomenon that you get out the other end of that is that if the day and the year are the same length, then the part of the planet that's facing the star will always be the same. So the planet, if the star was looking at the planet doesn't rotate as far as the star can see. It's just always showing the same face. So if we've got this green and purple planet down here, and it goes around the star to the opposite side, in the case of Earth, you have no idea what it's going to look like because it spins around so fast that you could easily draw like North America on the left. Like you could easily draw North America on the left and Asia on the right, or you could draw Asia on the right and North America on the left, like 12 hours apart, and it doesn't look out of place for Earth whatsoever. For a tidally locked planet, the same side of the planet always faces the star, which means that when we get over to this side, the green rock part of the surface is still facing the sun, or the star. So it would look something like this. And then we've got the purple rock on the other side of the planet that is facing away from the star. And so we end up getting this really interesting thing going on that if you look at this, and here's why I colored it the way I did, is so that the green and purple don't necessarily mean hot and cold when you just look at it, right? But if you think about it, if you've got this planet and the green side is always facing the star, it's always like noon on the green side, it's hot, right? Noon is a hot time of the day. Maybe not the hottest, you guys could argue it's like 4 p.m. or whatever, but noon, hot time of the day, the sun is overhead, right? And it's always overhead. It doesn't cool down at night. It just stays hot and gets hotter because the star is always in the sky, right? The sun is always up, if you will, for the green part of the planet. For the purple part of the planet, the sun never comes up. The star is always below their horizon, right? Because it's the purple side of the planet is pointing out that way into space, into deep space, into the blackness of the night sky. It's cold. It gets cold at night, right? Here on Earth, it gets hot during the day and then cools down at night. And even like regardless of where you are, sure, in some places in winter, you end up having like, oh, the clouds make it warmer or colder depending on whether the clouds are there or not. But generally speaking, It's hotter during the day than it is at night. The temperature always drops in the evening and then goes up in the morning, right? So for the purple side of the planet, there's never any sun, right? And I could even draw this sort of like an intermediate picture to show you what I mean. If I draw a sort of intermediate picture of this planet, the green side is down here, still facing the star, right? And the purple side is up here, facing away from the star at all times, right? So in the case of a tidally locked planet, one side of the planet, so in this case the green half of the planet, is always looking at the star, and so it gets really hot and stays really hot, and the other side of the planet is always looking away from the star, right? Look at the purple side, it's always pointing away from the star, whereas the green side is always pointing towards the star. And so what that basically means is that when you have a tidally locked planet, one half of it is very, very, very hot, and the other half is very, very, very cold, right? And so that's the problem that you run into with tidally locked planets, is that you would think if you're too close to the star, the whole planet is just hot, all the water boils off. Not necessarily. If you get really close to the star and the planet gets tidally locked, one side is absolutely blazing, 400, 500, 600 degrees Celsius. The other side is freezing, minus 130, minus 150 degrees. It's like way colder than you would get if you traveled to Canada or Norway or Russia or even Antarctica. We've never measured a temperature on Earth colder, in the environment, colder than about minus 88, 89 degrees Celsius. And I'm telling you that a planet could be closer to its star and have minus 150 degree temperatures on its backside, on its nighttime side. And so that's another possibility if you're too close to the star and your planet gets tidally locked. Now, that being said, I'm gonna have to unfortunately erase this diagram. Well, I'll read the last bullet point out without erasing, and then I'll erase it so you can read it more clearly. There is the possibility that a ring would exist between these two extremes, so the extremes being the really hot side and the really cold side, in a sort of twilight zone where liquid water could exist. So here's how I'm going to explain that. Let me get rid of all the wonderful drawings here first, and then we will sort of re-explain how this could happen. So we're going to have to draw in our star again. I'm going to draw in the star right here. We're going to have to draw in the planet again. Let's draw the planet right here, nice and big. I know I've made the planet bigger than the star, don't worry about that. And suppose we've got our, our two sides of the planet. So we've got our green side here. And we've got our purple side here. So we remember from our discussion a moment ago that the green side of the planet is always facing the star. So it's always very hot, right? On the green side, it's going to be very hot, too hot for life. Too hot for liquid water, too hot for life. It's like the Sahara Desert on steroids. It's just not a good time. On the flip side, the purple side is always cold. Too cold for life, icy, frozen, dark. Dark is a big problem, no photosynthesis, right? If you had plants on that side, they would just starve because there's no sunlight. And if you had plants on the hot side, they would probably just fry and burn after the constant sun exposure. But so you've got the hot side and the cold side. But if you remember our discussion sort of in general about the nature of the Goldilocks zone, you've got a hot side of the solar system, which is too close to the star. You've got a cold side of the picture, which is too far away from the star. And then there's this region in the middle where it's just perfect. And so you could think about that and realize that there might just be this sort of intermediate region right here on this planet, right in here where I've sort of put these yellowy orange lines. There's this little region right here where it might just be not too hot, not too cold. And so you might have this sort of band of liquid water, a band where liquid water could exist running around the planet from pole to pole. And so the reason I've said a sort of twilight zone here is that this side is the hot side. You can effectively think of at this point on the surface, this is like noon. The star is directly overhead this point on the surface. On the flip side, this point over here is midnight, right? And so if it's noon on this side and it's midnight on this side, then it's sort of twilight, 6 a.m., 6 p.m. kind of times in this yellowy orange band in the middle, right? It's going to be right in between. If it's noon over here, then you could say it's like 6 p.m. or 6 a.m. kind of, that kind of brightness where it's like an early morning, late evening kind of look in the sky. And then it's midnight over there. And because the planet is always showing the same face to the star never moves in the planet's sky. So wherever it's noon, it's always noon. It always looks like that. The star never moves in the sky for that point on the planet. And if it doesn't look like noon and it looks like whatever, like 10 a.m. if you're in some other part of the surface where the sun's not directly overhead, it still never moves. So in this region where it's that sort of 6 a.m., 6 p.m. kind of brightness, and it's like a sunrise, sunset kind of look in the sky, it never changes. It always looks like that. So it's sort of like a twilight area where it's just always twilight. The sky's always dim and, the sun is like kind of up, but not really up at the same time. And in that zone, it might just be the perfect temperature for liquid water to exist. So even if you're too close to the star, there might be this little way to get liquid water on the surface. So we shouldn't rule that out as an option. It's just less likely to have life than a planet that's covered with water like the Earth. Now, on the flip side, what happens if you're too far from the star? So we just talked about if you're too close to the star, it's too hot, everything boils off, all the water boils off. And that's not necessarily true if your planet is tidally locked. But if your planet's not tidally locked, then it's basically just hot and you lose all your water, which sucks. But on the cold side, then it's too cold, all the water on the surface freezes, and tidal locking doesn't happen on the cold side. Like if you're too far from the star, tidal locking won't happen. So you won't run into a situation where the planet's really far away from the star, but one side always faces the star. Shouldn't it be warmer? Maybe it would work out that way if you could have tidal locking for a planet that was really far away from its star. But unfortunately, that doesn't happen. So that's not an option. And the reason it doesn't happen is that the way that the star pulls on the planet slows down its rotation from whatever different rotation it had. It slows it down until it's this exact 1 day equals 1 year rotation period. It's all the star's fault for slowing down the rotation until it gets to that point where the planet is tidally locked. But the thing is that the sun is able to exert such a strong pull on the planet to make it tidally locked because the planet is close. The farther away the planet goes, the less the star is going to be able to slow down the rotation in that way. And so you wouldn't get tidal locking in like an outer solar system planet. And actually you can, even if you look at our solar system, Earth's day is 1 day, obviously. If you go farther out to Jupiter, massive planet, enormous planet, its day is 10 hours long. So less than half the duration of our day. And it's an enormous planet, which means it's spinning really, really fast. And that's not to say that it's because it's far away from the sun that it spins really fast. It's just that it's definitely not being slowed down very much by the sun because it still spins around really fast. On the flip side, if you look towards the inside of the solar system, Mercury and Venus both have tremendously long days. Venus's day is longer than its year, and Mercury's day is just very long. So Earth's day is 1 day, obviously, 1 day, 24 hours. Mercury's day is the same as 59 Earth days, and Venus's day is like 240, 243 Earth days. So they both spin tremendously, tremendously slowly, Mercury and Venus. And I'm sure that part of that is due to tidal forces. But anyway, we don't see that in the outer solar system. We don't see that on planets that are beyond the habitable zone. So beyond the habitable zone, it's too cold. All the water on the surface freezes. It sounds like it's just cold, dead, miserable. There is a chance, though, of the possibility of life on moons. And so this arises from if we look at our solar system, we've got the example of moons that orbit large planets. So that would, for example, be Europa orbiting Jupiter or Enceladus orbiting Saturn. And these moons also undergo tidal forces, just like the tidal forces we were talking about with the star and the planet happens between planets and moons too. And in fact, it's why that same tidal force that like the star exerts on the planet, the moon is tidally locked to Earth. If you look at the moon and you look at a time lapse of the moon throughout its orbit, the moon always shows the same face to Earth. And so that means that the moon is tidally locked with Earth. And so that means if you went to the surface of the moon, Earth would basically be fixed in the sky. Now, I'm not going to get too much into detail on that just because it's difficult to think about. But if you went to the moon, because the moon is tidally locked with Earth, Earth would appear fixed in the sky. The reason the moon isn't fixed in our sky is that Earth is not tidally locked with the moon. Now, if this isn't making sense, then just ignore it. But basically, Earth isn't always showing its same face to the moon. It's the moon that's showing its same face to the Earth. I feel like that's going to sound really confusing, so if you're confused, just ignore that and we'll move on. If you want to know more, leave me a message, leave me a comment, and I will be happy to explain more. But anyway, so a moon like Europa or Enceladus that's orbiting a large planet like Jupiter or Saturn undergoes tidal forces. And those tidal forces stretch and squeeze the moon. So basically the moon will go from like this shape, obviously I've exaggerated that a little bit, to this shape, and then back to this shape. And so all the material inside is getting stretched and squished, right? So you've got the material here is being stretched and squished, and then here it's being squished this way, and maybe stretched that way, right? So all this stuff is moving, there's friction, and that generates heat. And so it is possible, even though it's a moon and it's in the cold part of the solar system beyond the habitable zone, this stretching and squeezing as the moon orbits its host planet generates heat, which could allow water to exist in a liquid form below the surface. So you might have like a shell, a surface of ice, and then an ocean underneath that. And so that's a possibility on these moons, and you could, in theory, get that in moons around planets or around other stars as well. Now, it's not guaranteed to happen with every moon, but it is a similar thing to what we saw on the previous slide in that even though you're beyond the habitable zone, there might be a little trick that lets you get liquid water anyway. In the part of the solar system where it's too hot, the trick is that little ring in the Twilight Zone. And here on the cold side, if you're where it's too cold, you're beyond the habitable zone, the trick is this tidal forces, the stretching and the squeezing on moons that orbit large planets. So within the habitable zone itself, or within the Goldilocks zone itself, a planet would basically be able to hold large quantities of water on its surface. So we saw in the hot case, there might be a way that it can have a little bit of water on its surface, but otherwise not really. On the cold side, you might have a ton of water, but it's all going to be in the subsurface. It's not as easy to reach. You know, if an organism ever reaches the surface of that planet, it's basically just going to die because there's no liquid water on the surface, and it would have to live in that subsurface ocean. Now, that ability of planets to support liquid water does depend in part on the star. and and how hot the star is and how far away the star is, but it also does depend on the planet to some degree with things like the surface pressure and stuff like that. We're not going to worry too much about that. We can basically think of it as how far away you are from the star dictates how likely it is that you have water on your surface, or at least how capable you are as a planet of having water on your surface. And as I mentioned before, the presence of water does not necessarily mean that life is also going to be present, and vice versa. You could have a type of life form that we just don't know about that exists without water somehow, and we just don't know how to even imagine that right now because everything we know of makes use of water. So the two aren't exactly the same, but because life as we know it, the life that we've seen and experienced here on Earth, because it depends on liquid water in some way, shape, or form, it is reasonable to consider that planets with the ability to also support liquid water are the best candidates for planets with life on them. So this point says, it is reasonable to consider planets with the capacity to support liquid water as prime candidates in the search for ET, for aliens, for extraterrestrial life. And so basically what that's saying is that the planets that are in their habitable zones of their stars have a greater chance of having liquid water on their surface. And as far as we know, having liquid water on your planet's surface gives your planet a better chance of having life on it. So that's why those are the planets that we look at. And just one final note, I just said here that planets that are in the habitable zones of their stars. That's an important note. It's that the habitable zone is something that by and large is dictated by the star, by the temperature of the star. In fact, it's not something that the planet gets to choose. It's the star creates this zone where planets could support liquid water, and it's up to the planets to live in that zone. So in the case of our solar system, it's actually kind of convenient how this works out. I mean, obviously it's convenient for us, but it's also convenient in terms of remembering where the sort of edges are. In our solar system, now obviously the distances between these planets aren't to scale, but the habitable zone basically ends on the inner side with the orbit of Venus, and on the outer side with the orbit of Mars. So basically what we have is, the sun is over here on the left, and then all of this space in here, if you have a planet there like Mercury or basically Venus, it's too hot. It's too hot for life. And the boundary of that, this red line, is basically Venus's orbit. Venus's orbit is a pretty good marker of the inner edge of the habitable zone. And then in this zone, you could have planets that do support liquid water and the potential for life. So that would be planets like Earth. And then that outer edge, the outer edge of the habitable zone, is more or less marked by the orbit of Mars. So this is the boundary beyond which it's too cold. And so that's a bit of a simplification, but it's a decent way of remembering where the bounds of the habitable zone in our solar system are. So if we had another planet that was between Venus and Mars, so like an even closer neighbor in space, that would also be a habitable planet because it would fall in the habitable zone. So that's kind of interesting to think about, but it does seem like Earth is the only planet in this part of the solar system. It does have some buddies in the form of asteroids and obviously the moon, but nothing that's of planetary size. And this is just a fun little graphic of another way that you can think of the habitable zone, because it's basically the area in which life can exist. So if life can't exist outside the habitable zone, that means there's no risk of getting attacked by a bear if you're on Mercury or Venus, right? There's no risk of getting attacked by a bear if you're out there. And there's no risk of getting attacked by a bear if you're out here, because if there's no life, then that means there are no bears on Jupiter or Saturn or Uranus or Neptune or Pluto or anything else that's way out there. So as much as Earth is great for life, we're also always at a comparatively really high risk of getting attacked by a bear, because we live on a planet that supports the existence of bears, which is not true of any other planet in the solar system. So as much as Earth is great for life, we're also under the greatest threat of being attacked and eaten by bears, lions, sharks, etc. Here, as compared to anywhere else, because there are no bears, sharks, lions, etc. on the other planets. And so this last point that I want to make is that the habitable zone can look different for different solar systems. And by that I mean that for different stars, the habitable zone will look different. So you can see here, if you look at these white rings in these different solar systems here, the white rings are all the same size. They're the orbits of planets, right? So we've got this one really little ring in the center. If we just look at this middle diagram here, we've got this one really little ring in the center, and then we've got a second one right there, and then we've got a third one, and then we've got this fourth outermost one. So if we think of that as Mercury, Venus, Earth, Mars, and that might actually be what it's trying to represent here. If we've got Mercury, Venus, Earth, Mars, if we look at sun-like stars, then we've got that really tiny ring in the center. That would be Mercury's orbit. So too hot to support life. Then the second ring right here, that's Venus's orbit, and it's just inside that red zone, but it's basically the border of the red and the green. The green is the habitable zone, and so we can see the third white ring, that's Earth's orbit, lives inside that green area, that's the habitable zone. And then the last one, Mars, is just at that outer border between the green and the blue. So it's just on that outer edge of the habitable zone into that colder part. If the sun was hotter, then you can see that the green portion actually moves outwards. Right? The hotter the star gets, the farther away you have to move from it to be at a comfortable temperature. You can think of it as like a campfire, right? If you have a really small fire, you have to get really close to it to get warm. If you have a really big fire, you kind of want to keep your distance from it so that you don't burn. And so if you had a really hot star, notice that the orbits, the little white rings, haven't changed in size. But for a hotter star, the first 3 orbits are all in the red zone. So that means that if the sun was hotter, Earth would be too hot for life, being where it is, and Mars would be the ideal place for life to exist. And if we had a colder sun, then the green section, the habitable zone, moves inwards towards the star, and so we'd end up with, you can see that the first ring is still Mercury's orbit, and then the second ring right there is Venus's orbit. So if the sun was a little bit cooler, Venus might have been an ideal candidate for life in our solar system, and Earth would have been in that blue area, and Mars would have been so far away and just so unbelievably cold. So you can think of it like a campfire, that if the fire gets bigger, you don't need to be as close to it to get warm, and actually being too close to it, you're going to feel hot. Whereas if the fire is really small, really weak, you have to get really close to it to stay warm. Right, so it's the same way with stars. The hotter the star is, the farther out the habitable zone moves. And basically that means that the hotter the star gets, if you stay close to it, you're just going to cook. And if the star gets colder and colder and your planet stays exactly where it is, then it's going to freeze. So in different solar systems, you'll have stars of different temperatures, and so those temperatures will dictate where exactly this habitable zone is. And then if you happen to find a planet that fits in there, that's a good candidate for life, because you have a planet that's in the habitable zone, and therefore, provided it's solid, has a chance of supporting liquid water on its surface, and that means a chance of supporting life as we know it. So that's all I got for you guys today. This lesson did end up being longer than I thought it was. It's definitely not something that's going to fit in just one of your classes, so you guys are probably watching this part in a second stint. But that's okay. We got through all the details of the project and the details of the Goldilocks zone. This picture has just got an example of what you guys might see when you go looking up the instruments that exist on space probes. So you'll see the kinds of names of the instruments here. You don't have to worry about what it means to have an occultation ultraviolet spectrometer on board. All you got to do is figure out what it does and then just explain that in normal human terms. But yeah, so these are the kinds of things you might see, and then hopefully some more detailed descriptions of what they actually do. But yeah, that's just a sample picture to get you guys sort of prepared for what you're about to see. I'm excited to see what happens with your projects. Until next time, have a good one.